Hello students, today's topic is Green's theorem, its verification and its application in finding line integrals or finding area under a closed curve, etc. So first, what is Green's theorem in the plane? Let capital D be a closed and bounded region in the xy plane which is quadratic with respect to both the axes. Quadratic with respect to both the axes. Or can be split up into a finite number of regions quadratic with respect to both the axes. And let capital C be the closed oriented boundary curve of D, and f vector is equal to small f of xy I cap plus small g of xy j cap is a continuous vector point function having continuous first order partial derivatives at each point in the region D and on its boundary curve, closed curve, boundary curve C. Then line integral f vector dot dr vector over the curve C, closed boundary curve C, is equal to double integral over the region D curl f dot k cap dA. dA is actually dx dy. R vector is xi cap plus yj cap is position vector of any point in the region D. That means it is the relation between line integral and double integral. Sometimes line integral difficult to find, so in that case we shall find the double integral. So Green's theorem in the plane is actually connection between line integral and double integral. Line integral is taken over the closed boundary curve of the region D, and unless otherwise stated, the curve C is traversed in positive sense. That means for a simple closed curve, it is traversed in anti-clockwise sense. So there is another for quadratic with respect to both the axes, means any line parallel to y-axis or parallel to x-axis meets the boundary of the region D in at most 2 points. That is called quadratic with respect to both the axes. Okay, so this is Green's theorem in the plane, connection between line integral and double integral. Now this is vector form and Cartesian form. Let us deduce here. R vector is xi cap yj cap, position vector of any point in the region D. So dr vector is dxi cap plus dyj cap. F vector dot dr vector is small f I cap plus gj cap dot dxi cap plus dyj cap. If we take dot product, we get f dx plus g dy. And curl f del cross f, curl f vector is determinant form is written like that: I cap j cap k cap del by del x del by del y del by del z, partial derivative operator. Okay, f g 0, third component is 0 here for the function f vector. So it is just del g by del x minus del f by del y into k cap, because other parts are 0. See, del y of 0 will be there, del z of g is 0 because g do not contain z, so I cap part is not there. Similarly for j cap part, it is del x of 0 minus del z of f, there is no z in f, that's why other parts are 0. So this is curl f. Now curl f dot k cap is surely, obviously if we take dot with k cap, it is just del g by del x minus del f by del y. So curl f dot k cap is del g by del x minus del f del y. Therefore the line integral of f vector over the closed curve C, when the integral is taken along a closed curve, this circle symbol is given in the middle of the integral symbol. Okay, so line integral of f vector over the closed curve C is equal to double integral of curl f over the region D dot k cap dA becomes this line. Green's theorem in vector form becomes, left side becomes f dx plus g dy, and here it becomes del g by del x minus del f by del y, and dA is dx dy, area element in the xy plane. So this is Green's theorem in Cartesian form. So we shall use also this form. Now finding area by line integral, application of Green's theorem also. If D is the region in the xy plane quadratic with respect to both the axes, or can be split up into a finite number of subregions, quadratic with respect to both the axes, and C is the closed boundary curve of D, or D is a simply connected region bounded by a simple closed curve C. Simply connected region bounded by a simple closed curve C. The curve which does not intersect itself is simple. Okay, means the curve is not like that. This is also a closed curve, starting and end point same, but it is not it is not simple because it is cutting itself. It should be like that, maybe circle, maybe ellipse, anything. Okay, so if the area is bounded by simple closed curve C, this region D, boundary curve of D is C, then taking f of xy equal to minus y and g of xy equal to x, in Green's theorem we get this line integral becomes del g by del x minus del f by del y. This time what? G is x, just x, so del g by del x will be 1, and f is minus y, so del f by del y will be minus 1, so 1 minus minus 1 means 2, and left side becomes minus y dx, f is minus y, g is x, x dy, and here it becomes x dy minus y dx. So line integral over C, the integrand is here x dy minus y dx, and right side is 2 taken out, dA, double integration over of the region D, the function here is 1, so it is area of the region D, double integration dx dy or double integration dA, it's simply dA is there, then it is the area of the region D. So area of the region D become bounded by curve C becomes what? Half line integral x dy minus y dx over the curve C. C is the boundary of the region D. Okay, if this is the region C, a boundary curve C, and this is D. Sorry. This is D, region bounded by C, and it is traversed in anti-clockwise direction. So by line integral also you can find area of a closed region. Now let us see example number 13, continuation. Evaluate this line integral cos x sin y minus xy dx plus sin x cos y dy over the curve gamma. Here symbol is given gamma instead of C, closed curve. Evaluate this using Green's theorem, where gamma is the circle x square plus y square equal to 1 in the xy plane, described in the positive sense, means it will be in anti-clockwise sense. So let D be the region bounded by the circle gamma whose equation is x square plus y square equal to 1, having center at origin and radius 1. Center, origin, radius 1. Okay, now this line integral, given line integral, this is f dx plus g dy form, so we shall write it is in Cartesian form. So double integration over D is equal to del g by del x, g is here coefficient of dy, sin x cos y, so del by del x of sin x cos y minus del y of f, f means here cos x sin y minus xy, given dx dy. Okay, so this is partial derivative with respect to x, sin x derivative with respect to x is cos x, y constant here, so del y of this sin x cos x sin y derivative is cos y, and xy derivative will be only x, and this minus minus plus, so you have got this. Now this is cos x cos y gone, what remains only x, so double integral of x over the region D, and see this is the circular region, D is this region bounded by C is our D. The circle is described in anti-clockwise direction, and this region can be described by strips parallel to y-axis from y equal to minus root over 1 minus x square to y equal to root over 1 minus x square. From the circle, this equation we get y square equal to 1 minus x square, y is plus minus root over 1 minus x square, so limits for y minus root over 1 minus x square to plus root over 1 minus x square, vertical strip, and then this strip is to be moved from x equal to minus 1 to x equal to 1 to cover the whole region. So that's why the limits of integration are here, x minus 1 to 1, y minus root over 1 minus x square to plus root over 1 minus x square. So first we integrate with respect to y because limits of y are variable, so just 1 dy, so it will be y upper limit minus lower limit will make it this minus minus, that means twice root over 1 minus x square, so it is the single integral. Now here root over x into root over 1 minus x square dx. See, this is an odd function. If you replace x by minus x, it will be minus of this function again, means it is odd function, and integration limits are minus 1 to plus 1. So by the property of definite integral, the integral is 0. So we have found the value of this integral, line integral rather, using Green's theorem easily. Next, example 31. Verify Green's theorem in the plane for this integral, line integral. Verify. We have to verify means we have to calculate line integral and we have to calculate corresponding double integral and see whether they are same or not. So where gamma is the boundary of the region enclosed by y equal to x square, y square equal to x, means two parabolas described in the positive sense. So let D be the region bounded by the closed curve gamma defined by y square equal to x and x square equal to y, which are two parabolas. So figures are that this is y square equal to 4x type, this is x square equal to 4y type. So here f of xy from the given integral f is twice xy minus x square and g is x square plus y square. So this is written here. Therefore, let us find the double integral first. Right side of Green's theorem. Double integration over d del g by del x minus del f by del y. That is equal to del g by del x. G is here x square plus y square. So it is twice x. And del g by del y, derivative of y with respect to y is 1. So it will be only twice x. So twice x minus twice x. Integrand is 0. So the answer is 0. Double integral answer is 0. So we should get this time line integral along the boundary curve gamma is also 0. We have to verify. So the boundary curve gamma of the region D consists of two curves C1 and C2. Two curves C1 and C2. C1, let us name this part OAB. OAB. This is OAB. Arc of one parabola. Means this is x square equal to y parabola. X square equal to y or y equal to x square. And then another part C2 BEO. This is BEO. This part is we are marking C1 and this part is C2 BEO. Corresponding to y equal to x square and y square equal to x respectively. Two parts, different types. Now along C1, C1 means OAB. Y equal to x square. This parabola is y equal to x square. Therefore, dy is twice x dx and x varies from 0 to 1. See, these two parabola, if we solve line number, this 1 and 2, if we solve, obviously we shall get 0 and 1. See, y is x square. So if we y is x square, here y square is x. So if we square it, x to the power 4 will be y square, means y square is again x if we put. So x to the power 4 equal to x means x into x cube minus 1, 0. So roots will be 0 and 1. Okay. So x varies from 0 to 1. Origin to B, point of intersection here 1. So 0 to 1. Now fxy is twice xy minus x square, but here y is x square, so it is twice x cube minus x square, and gxy is x square plus y square, but y square is here x to the power 4. So it is written. Therefore, line integral along the arc C1, part C1, it is not closed curve. Therefore, not circle is given. It is just arc of the parabola. So line integral along C1 is f dx plus g dy becomes f is this calculated, g is that calculated, and dx is that, dy is twice x dx substituted value. So final simplification gives this 4x cube minus x square plus 2x to the power 5 dx. Integration with respect to x single variable. So it is x to the power 4 by 4, 4 gets cancelled, then x cube by 3 plus 2x to the power 6 by 6 means 2 is there, so 1 by 3. So 0 to 1 limit means if we put x equal to 1, it will be 1 minus 1 by 3 plus 1 by 3 means just 1, and when 0 all 0. So 1 final along C1, line integral along C1 we have got 1. Now line integral along C2 we should get minus 1 so that the value becomes 0, because already we have got double integral 0. So here what we do along C2 means along BEO, along this is the parabola y equal to 4x. So y equal to root x here, and x varies from 1 to 0 for complete circuit. So along C2 means BEO, y square is x, dx is twice y dy, and x varies from 1 to 0, y also varies from 1 to 0. When x equal to 1, for these two curves point of intersection y is also 1. When x is 1, y is 1. So this time we shall convert to y, means line integral will be calculated converting x to y. Okay, all expressing in terms of y. So y varies from 1 to 0. B2 origin fxy is twice xy minus x square. Here y square is x, means x equal to y square. So it will be 2y cube minus y to the power 4, because x is y square. Gxy is x square plus y square, means x square will be y to the power 4. So line integral along C2, not a closed curve, just part of the parabola. F dx plus g dy becomes 1 to 0. This is important. Integration limit 1 to 0, lower limit 1, upper limit 0. And our f is, if we take f is f, sorry, f dx, we have calculated 2y cube minus y to the power 4, yes, and dx is 2y dy, so 2y is written here, dy plus g dy, g is y to the power 4 plus y square dy, okay, is equal to integration 1 to 0, simplify 4y to the power 4, there is y to the power 4, 5y to the power 4, yes, and then minus 2y to the power 5, and then 5 plus y square, okay, simplification done. Now integration y to the power 4, integration y to the power 5 by 5, so this 5 gets cancelled, so it is only y to the power 5, then y to the power 6 by 6, 2 by 6 will be 1 by 3, and then y cube by 3 means 1 by 3 y cube, correct. So when upper limit is 0, all 0, when lower limit is 1, substituted 1 minus 1 plus 1, yes, so it becomes minus 1. When we put lower limit, minus to be given, so minus 1 got. Therefore the total line integral along the curve gamma f dx plus d dy, the expression under line integral, is equal to line integral along c1 of the same expression plus line integral along c2, properties of line integral, okay. So adding these two, we get 1 and minus 1 added means 0, and already you have got double integral 0, therefore line integral equal to double integral, means Green's theorem is verified, okay, verification of Green's theorem. Example number 32, similar question. Verify Green's theorem in the plane for this integral, line integral, integral over gamma x square dx plus xy dy, where gamma is the square in the xy plane given by x equal to 0, y equal to 0, x equal to a, y equal to a, where a greater than 0, described in the positive sense, that is in an anti-clockwise sense. So here D is the region bounded by the given square whose boundary curve is gamma. Here fxy is x square, see x square, f dx x square, and gxy is xy, okay. So double integral, let us calculate first. Double integration over D is equal to double integration del g del x. Del g del x is just y minus del f del y. Del f del y is 0 because we are only x square. So y, double integration over D of the function y. Dx dy is there for symbol for differential in double integral. Now this is the region y equal to 0, y equal to a, x equal to 0, x equal to a. Region D is, this is the region D bounded by the square. So here y varies from 0 to a, x also varies from 0 to a, obviously. So limit for y 0 to a, limit for x 0 to a. Double integral expressed as repeated integral, and we get y integration with respect to y is y square by 2, 0 to a, half is there. So if we put a, means s square by 2 minus 0, okay. So again if we integrate, it is just dx means x, limit 0 to a means only a will be coming, so a cube by 2. So you have got double integral a cube by 2. Now we should get the line integral also a cube by 2. There are 4 parts of the boundary curve gamma. The boundary curve gamma of D consists of 4 smooth parts. All parts are smooth, 4 parts, OA, AB, BE, EO. So separately we have to calculate. Along OA, what we see, this is along x-axis, means y equal to 0, and x varies from 0 to a. fxy is x square. See what is fxy? fxy is x square, gxy is xy. fxy is x square and gxy is xy, but y is 0, so that's why gxy is 0. Therefore line integral along the part OA is equal to f dx plus g dy becomes here only x square dx, because g is 0. So it is simple integral, x cube by 3 means a cube by 3 will be coming. Then along AB, what we notice, AB is the line, is a line parallel to y axis. So the x equal to a always we have, and y varies from 0 to a. Y varies from 0 to a. So we have written here. So fxy is x square, means it will be a square, x is equal to a always constant. Gxy is xy means here ay. Dx is 0 because x is constant. So line integral along AB becomes f dx plus g dy becomes s square into 0 plus ay into dy, ay dy. Okay. So because dx is 0, that's why. So it will be integrate, it is y square by 2, means it is a cube by 2 will be coming. Got. Along B, what do you observe along B? Along B, y equal to a, and x varies from a to 0. Here x is a, here 0. So what you get, along b y equal to a, dy 0 because y constant, and x varies from a to 0. There fxy is x square, gxy is xy means here a, y is a. Therefore line integral along be becomes f dx dy becomes integration a to 0. Important, this is a to 0, lower limit a, upper limit 0, x square dx, because dy is 0. So it is again x cube by 3 means 0 upper limit, that's why minus a cube by 3, 0 minus a cube by 3. Along EO, what we observe, EO, x is 0, y varies from a to 0. So along EO, x is 0, dx is 0 automatically, y varies from a to 0, fxy is 0 because x square it is 0, gxy is xy is also 0 because x is 0. So finally line integral becomes simply 0 because functions f and g both are 0. Therefore line integral along the curve gamma, it becomes line integral along OA plus line integral along AB plus line integral along B plus line integral along EO. So all the values added, and finally we get a cube by 3 plus a cube by 2 minus a cube by 3 means this cancels, a cube by 2. What we have got, double integral we have got a cube by 2. Okay, so this is equal to double integral, means line integral equal to double integral. Therefore Green's theorem is verified. So next example 33. Evaluate using Green's theorem the integral, means this is a line integral in vector from given f vector dot dr vector, line integral along the closed curve C, where C is the ellipse boundary of the ellipse. So we have to calculate this line integral using Green's theorem, means we have to calculate double integral over the region D bounded by C. So here r vector is xi cap plus yj cap is position vector of any point, dr vector is dxi cap dyj cap, then the line integral, this sin yi cap plus x1 plus cos yj cap dot dr vector. So if you take dot with dr vector, we get sin y dx plus x into 1 plus cos y dy. Okay, dot product. So let us denote this as f dx plus g dy, say. Therefore by Green's theorem we get double integral over d is equal in of the function del g by del x minus del f del y, where d is the region bounded by the ellipse x square by s square plus s square by b square equal to 1, that is bounded by C, and this we get by using Green's theorem. So this is D mentioned. Okay, now here del x of g means our x into 1 plus cos y, del x of x into 1 plus cos y minus del y of f means sin y. Okay, so derivative of x with respect to x1, partial derivative, so 1 plus cos y only, minus del y of sin y is cos y. So sorry, sin y cos y gets cancelled here, not sin y, sorry, cos y and minus cos y gets cancelled, 1 remains. So double integration over the region D dx dy, function is there 1, and that we know it is nothing but area of the region D, so that is area of the ellipse. But area of the ellipse we know pi AB, a and b are lengths of semi major axis and semi minor axis, all of you know. So this line integral becomes area of the ellipse, and it is pi AB. So using Green's theorem we have found easily. Next example, evaluate using Green's theorem the line integral along the closed curve C. The function is here x square minus cos hyperbolic y dx plus sin x cos y dy, where C is the rectangle with vertices 0 0 pi 0 pi 1 0 1. So this is 0 0, this is pi 0, this is pi 1, this is 0 1. Okay, so line integral, it is like f dx plus g dy. So by Green's theorem we get del g del x minus del f del y, the expression, and it becomes double integral over D, where D is the rectangular region bounded by C. This region is D. Okay, so by the del x of g means here, what is that, sin x cos y, and f means here x square minus cos hyperbolic y. Okay, so del x of this minus del y of that. So sin x derivative is cos x cos y it, and then x del y of x square is 0, minus plus derivative of cos hyperbolic y with respect to y is sin hyperbolic y, no minus sign for hyperbolic, this is hyperbolic function. So what it becomes, this rectangular region here, y varies from 0 to 1, and x varies from 0 to pi, obviously. Y varies from, here y is 0 and here y is pi. Y is pi. So limit for y 0 to pi, and here x is 0 from y-axis, here x equal to 1. Sorry, x 0 to pi, it should be pi. X 0 to pi, y 0 to 1, y 0 to 1, this is 1. See the vertices 0 0 pi 0 means x 0 to pi and y 0 to 1. Okay, what is written? Y 0 to 1, correct? X 0 to pi. The coordinates better we mention here. Coordinates, this is pi 0, this is pi 1, and this is 0 1, but as given in the question. So integration of the function, first let us integrate with respect to y. Cos x cos y. Cos y integration is sin y, and sin hyperbolic y integration with respect to y is cos hyperbolic y. Okay, no minus sign. So y 0 to 1 means if we put, this is the result written, integration of sin hyperbolic y is cos hyperbolic y. So when y is 1 sin 1, when y is 1 cos hyperbolic 1, minus when y is 0 sin 0 will be 0 and cos hyperbolic 0 is again 1. So you get cos 1 cos x sin 1 plus cos hyperbolic 1 minus 1. Cos hyperbolic 0 is 1, sin 0 is 0. So this integral now becomes with respect to x only, 0 to pi. So cos x integration sin x, sin 1 is constant, cos hyperbolic 1 constant, 1 constant. So it is x is there only. So upper limit pi means sin pi, sin 1 minus, sorry, plus cos hyperbolic 1 minus 1 into pi. And when 0, sin 0 is 0 and here is 0. So we have not written. So it is pi cos hyperbolic 1 minus 1 and sin pi is 0. So this is the answer. Okay, so using Green's theorem we have found this line integral, means we have calculated double integral only. Example 35, find the area of the ellipse using line integral. We know area of this ellipse, standard ellipse, area is pi ab, but prove it using line integral. Parametric equation of the ellipse is x equal to a cos theta, y equal to b sin theta, because this satisfies the equation. X by a is cos square will be cos square theta, y by b square will be sin square theta, cos square theta plus sin square theta, 1 theta is parameter. So this is parametric equation of ellipse. Theta is parameter and theta varies from 0 to 2 pi to cover the whole ellipse. Okay. X is a cos theta, y is b sin theta, dx is minus a sin theta d theta, cos theta derivative minus sin theta derivative is cos theta, so dy is b cos theta d theta. Therefore area of the ellipse, we know area of the closed curve is given by half line integral x dy minus y dx under integral symbol and over the curve c. See the closed curve here. This is the formula we have proved also, okay, using Green's theorem. So this is 0 to 2 pi to cover the whole curve, boundary curve, starting from a in anticlockwise direction coming to a is theta 0 to 2 pi. So x is a cos theta, dy is b cos theta d theta, and y is b sin theta, dx is minus a sin theta d theta. That's why this minus becomes plus a sin theta d theta. Okay, equal to ab common, half is already there. It is cos square theta plus sin square theta. Okay, so it is 1 again. So half ab integration 0 to 2 pi d theta means just theta integration 1 d theta is theta, 2 pi minus 0 means 2 pi. So we have got pi ab square unit. So area of the ellipse we know pi ab square unit, but it is proved with the help of line integral easily. One note, if we take x equal to au and u is r cos theta, y equal to bv and v is r sin theta, then dx dy becomes abr dr d theta. Jacobian will be abr under this transformation. Okay, and ellipse x square by s square plus s square by b square equal to 1 will become what? X by a will be u y by b will be v means u square plus b square 1, but u is r cos theta, v is r sin theta, means ultimately r square equal to 1. So r equal to 1, which is a circle in UV plane for which r varies from 0 to 1. This is r varies from 0 to 1 and theta from 0 to 2 pi for a circle with center origin radius 1. Therefore, area of the ellipse using double integral is given by double integration over d dx dy, means dx dy is abr dr d theta over the region d dash, means elliptic region becomes circular region. It is the region in UV plane. D dash we have symbol given. Change of variable we have used, so it is integration 0 to 2 pi d theta and r limit 0 to 1, so r dr, because they are limit constant and separately we can integrate. So finally we have got pi ab square. It means this is without using Green's theorem also we can find the area of the ellipse using change of variable in a double integral, area given by this double integral. Here d dash is region bounded by the circle in UV plane and d is the region bounded by ellipse. So elliptic region becomes circular region under this transformation, and easily we have found the area. So this is direct way, and that is line integral using Green's theorem we have found. Okay, application of Green's theorem actually gives this formula. So thank you for today, and some this writing error are there. I shall correct this in PDF. Thank you.